In computer science, logic refers to the use of formal logical systems to represent and reason about computational processes. It focuses on the principles of reasoning using symbolic expressions to model and analyze problems. By applying logical rules and structures, computer science can ensure consistency, correctness, and efficiency in algorithms, programming languages, and systems design. Propositional logic or Boolean logic is a branch of formal logic that deals with propositions. Propositions are statements that are either true or false. No ambiguity. Unlike everyday reasoning, propositional logic uses clear, well-defined rules. For an example, proposition 1, the file has been saved, true or false. Proposition 2, the program executed successfully, true or false. So logical connectives, propositional logic combines individual propositions into complex statements using logical operators. For example, and or not. For the application, it serves as the foundation for computational processes. The importance is an essential tool in computer science for analyzing relationships and making decisions. Next is why is propositional logic is important in computer science. So one of the reasons is formal reasoning. It provides a systematic way to model and analyze computational problems, ensuring algorithms work correctly in different scenarios. Second, algorithm design. It uses logical rules to create decision-making algorithms and automate problem solving. Thirdly, programming constructs. Control structures, for example, if-else statements, loops, are based on propositional logic, ensuring predictable and reliable code execution. And fourth, digital circuit design, where the logical operations like and or not are fundamental in designing digital circuits that power computational hardware. And lastly, verification and validation. The propositional logic helps verify the correctness of software and hardware systems, ensuring they meet specifications. So in conclusion, propositional logic plays a vital role in creating efficient, reliable computational systems.
Let's talk about key components of propositional logic. Propositional logic is built on several fundamental components that enable logical reasoning and decision making. These include propositions, logical connectives, truth table, and the concepts of syntax and semantics. Proposition means a simple statement that can either be true or false. For example, the program is running is a proposition that is true if the program is running and false if it is not. Propositions serve as the basic units of propositional logic, which can be combined to form more complex statements. Secondly, logical connectives. Logical connective combines propositional to create more complex expressions. Common connectives include and, which can be true only if both statements are true. Second one will be or, where in this case it will be true if at least one statement is true. Lastly, we have not, where it negates the truth value of a statement. And then we also have implies, where it's true unless the first statement is true and the second statement is false. For instance, if P is the program is running and Q is the database is empty, we can form expressions like P and Q or P or Q to represent relationship between them. We have truth tables next. Truth tables are used to evaluate logical expressions by listing all possible truth values for individual propositions. They show the resulting truth value of the compound statement for every combination of true or false values. For example, for P and Q, the result is true only when both P and Q are trues. Lastly, we have syntax and semantics. Syntax defines the rules for creating valid logical expression, ensuring they are well formed. Semantics, on the other hand, assigns meaning to these expressions by specifying how truth value are determined for propositions and compound statements. Syntax ensures logical expressions are properly structured, while semantics ensure they are meaningful and interpretable. These components form the foundation of propositional logic, enabling it to model and evaluate logical statements for reasoning and problem solving in computer science, mathematics, and artificial intelligence. Propositional logic works by evaluating logical expression based on the truth values of the individual proposition that make up those expressions. The process follows a systematic approach where the propositions are identified, combined using logical connectives, and then evaluated through truth tables. The first step is to define the proposition. There are the basic statements that can be either true or false. For example, in the logical expression, it is raining and I will take an umbrella. Each of these statements represents a proposition with a truth value assigned to them. Next, logical connectives are applied to combine these two individual propositions into more complex logical expression. Common logical connectives includes and, or, not, and implies. For instance, the expression if it is raining, then I will take an umbrella uses the implication connective, which states that if proposition P is true, then proposition Q must also be true. Finally, truth tables are used to evaluate the truth value of the entire logical expression. A truth table lists all the possible combination of truth values for the individual proposition and determine the corresponding truth value of the compound statement. For the expression if P then Q, a truth table will show all possible combination of truth values for P and Q and how the truth value of the logical implication changes accordingly. The truth table helps us understand the condition under which the compound statement is true or false. Through this process, propositional logic provides a structured way to analyze and reason about relationships between statements, ensuring that conclusions drawn from logical expressions are valid and consistent. In propositional logic, logical operators are used to combine and manipulate propositions to form complex logical expressions as shown in the slides. These logical operators are the building blocks of propositional logic, allowing for the creation of intricate logical expression that can be used to model complex reasoning and decision-making process. By combining these operators, propositional logic enables a detailed analysis of condition, relationships, and dependencies within various systems. The structure and formal nature of propositional logic makes it foundational in computer science, particularly for algorithm design, programming, and also system verification. Understanding how these operators work is essential for tackling a wide range of computational challenging, as it will be explored in subsequent section.
Moving on, I will be explaining to you about the examples that we provide. So there are two examples that we provide for these presentations. So the first questions, the questions are: consider the following logical formula. The first one is P implies Q, second one is Q implies R, and the third one is P. So the question asks, determine whether R is true, false, or indeterminate. So for these questions, what we can do is, the first step that we can do is to analyze the premise. So we list down all the premises that have been given to us. So and then we can apply modus ponens that states if A implies to B is true and A is true, then B must also be true. So then from there, since third premise state that P is true, then we can conclude that Q is also true from premise 1. Then, if Q is true from premise 2, then we can conclude that R is also true. So from that, we can deduce that R is true. So our final answer will be R is true. Next, for question number 2, the questions asks us, prove that the following logical expressions are equivalent. The expressions are P implies to Q is equivalent to negate P union with Q. So if you remember, the definition of equivalence are two logical expressions A and B are equivalent if they have the same truth value for all possible combinations of the truth values of their variables. So what we can do from here is we can construct a truth table to determine the truth value for both expressions. And then, from there, we can conclude that P implicit Q is equivalent to negate P union with Q, because when we construct the truth table, we get all the results have the truth value are the same, which is they all are true.
Logic programming is a programming style that uses formal logic to express computations through facts, rules, and queries. Instead of specifying step-by-step instruction, it defines what is true and lets the system infer how to reach a solution. Prolog is a well-known example where developers create rules to define relationships between data and the system uses inference to answer queries. This approach is particularly useful for tasks involving reasoning, such as in knowledge-based systems like medical diagnosis or legal reasoning, where it helps automate decision making. Logic programming is also key in artificial intelligence, or known as AI application, like puzzle solving, chatbots, and natural language processing, enabling machine to reason about language and context. Its ability to handle complex reasoning based problems making logic programming a powerful tool across many fields.
Today, I will be talking about two important topics, mm, automated verification and digital circuit design, and I will explain their significance in real-world applications. The first one is automated verification. Automated verification uses logic to ensure the correctness of systems by checking if they meet specified properties. This process is widely applied in various fields, especially in safety-critical systems where reliability is essential. It's used in many areas, like aviation, nuclear reactors, and medical devices, ensuring the correctness of control systems is vital. Automated verification employs logical reasoning and more model checking to guarantee the stability and safety of these systems. And it also uses software development. During the early stage of software development, automated verification helps developers identify potential bugs and ensures that the code complies with logical specification. This reduces maintenance cost and improves the overall stability of the system. And the second one is digital circuit design. The digital circuits operate on binary values 0 and 1, which correspond to logical values of false and true. Boolean algebra, a subset of propositional logic, forms a theoretical foundation for designing and optimizing these circuits. So, why is Boolean algebra important? Boolean algebra helps simplify and optimize circuit design through logical operations, making digital systems faster and more power efficient. Whether it's computer chips, smartphones, or other electronic devices, they all rely on the principles of Boolean algebra and digital circuit design. In our daily lives, many of the electronic devices we use rely on microprocessors to operate and control their functions. For example, in smartphones, computers, and other digital devices, microprocessors are responsible for handling data input and output, storing information, and performing complex algorithmic computations. So, mm, to achieve these functions, we need to create efficient microprocessor architectures and optimize circuits to reduce power consumptions or enhance performance. This is one of the core goals of microprocessor design. By simplifying circuit structures and improving their efficiency, we can develop more powerful and energy efficient computing systems. Yeah, these are the three books we refer to, and thanks you all for your time and attention.